All right. I'll briefly give this talk. I'm a nuclear engineer, and I am very much a high-level requirements kind of guy. And this talk is all about why food is such an important factor in the future of space travel, because we take that guy there, the sun, for granted. For every person on Earth, we have about an acre of land. Do you know how much sunlight hits an acre of land? We're talking about a gigawatt of energy during the noon sun. So, you know, when we look at things like Mars, traveling to Mars, this is a specific case study. Elon Musk is saying he's sending 100 people per ship. So, you know, there's about 100 to 150 metric tons per ship. There's 2.1 years per opportunity. So every time Earth and Mars come together, you can launch a ship. And depending on your caloric intake, you can eat fat, carbs, and protein, but a balanced diet using the minimum possible, calories per gram. If you had pure carbs, pure fat, and pure protein with no water, no cellulose, no waste products, minimum of 300 kilograms a person for food for each of these opportunities. And in reality, you're looking more like a metric ton. So each of us, every 2 years, eats about a metric ton of food. No joke. Actually, we probably eat more on Earth because the water's in it. So if you send 100 people to Mars, you need to send 60 metric tons of food with them to last. And you can imagine how well that's going to go with Elon Musk's space plan if he's going to send 100 people and doesn't have room on a spacecraft to feed them their 60 metric tons of food that they need. So the logical conclusion is that anything beyond about 20 people will require native food production. You just can't, you send 6 astronauts if you're NASA, you don't need native food production. You send 20 people, the second you send that many people, it's not sustainable. So here's kind of where we look at power. I was talking about why we need food in terms of mass, but now we talk about power. See those lights up there? Grow lights, grain. Well, humans are surprisingly low power. We only need about 100 watts, which used to be about the power of a light bulb. We need a little bit more power than current light bulbs that are more efficient. So when we eat food, the amount of food that we eat, edible hydrocarbon bonds, our body is pretty bad at digesting them. We eat it and only about 20% of it is of the actual caloric value of burning it. If you burn it in a calorimeter versus eating it, you only get about 20% of that in your actual metabolism. Then you look at how much is edible. When a plant produces its hydrocarbon bonds, there's only so many of those hydrocarbon bonds that are actually edible. So that's an inefficiency. Then we jump to photosynthesis. Photosynthesis is actually incredibly inefficient. In many plants, you have less than 2% efficiency for photosynthetic efficiency in terms of sunlight to actual hydrocarbon bonds. And in the best plants we have, like grain, corn, potatoes, notably the ones that we eat a lot, and provide us our calories, so that can jump up to around 10%. And if you use special grow lights that don't have green lights in them, you can maybe get that up to 15%. But photosynthesis is pretty bad. And then when you look at engineering this, you talk about, let's build a facility, it needs to have airflow, it needs to have water, it needs to have all these other things. Now you're talking 60 kilowatts of energy. So the basic fundamental fact is growing food in space will require 100 times the energy of what we currently use on Earth. On Earth, we have about a kilowatt of electricity in the US per person, and about 10 kilowatts if you include all transportation and all sources. But in space, you're probably going to need more like 100 kilowatts per person, and that's if you're just going to be a vegetarian and eat the most basic food groups. So, in terms of our Mars case study, going back to it, each person, you need on the ISS about 10 kilowatts of environmental control and life support. And that, from what I understand, is expected to be fairly constant when you go to different locations in the solar system. The basic processes are very similar. But you need 100 kilowatts of food production. to put this in perspective, the Starship, the big rocket that Elon Musk wants to put on the surface of Mars, that one is, if you have it there for 2 years and you have a megawatt of electricity, you can refill it. You can use atmosphere and water, and you can turn it into rocket fuel. So every Starship would need about a megawatt of energy over the 2 years that it's there, to refill it, or a little bit less than 2 years because it has to leave sooner. But if you get 10 people on the surface of Mars, their food growing requirements outpace the propellant production requirements in terms of power of the actual big Starship. So you need a lot of power. And even when you talk about industry, like growing, making plastics, making concretes, all these types of things, that's going to be not the driving energy requirement. Food will be the driving energy requirement once you get very many people. There's a few studies that I encourage you to look at. These are some of the best ones I found. One of them is from Bryce Meyer, who's in the room. In the back there. He's actually the brilliant genius, because my background is not biology, my background is engineering, and he did a lot of the work that helped me prove this point. And another one I want to point out is a study that came out of Biosphere that was looking at growing food on Mars using, they actually built in Santa Fe a little place where they were growing food using light, and they published on it, and it was based on the Biosphere project. So in some of the Biosphere project, I just want to mainly point out the bottom graph. I won't have time to go to it in detail, but as you increase your photon flux, as you produce more photons, your plants grow proportionally faster until you reach a certain limit, and that's usually when you burn your plant. So what they found is that instead of having a really large building that's pressurized, you can have a very small building and just shine up to about 10 times more light than solar light on top of it, and you could get it to be mostly efficient. The efficiency drops as he goes up. So there's some people who looked at this, and Bryce has some great results where he looked at different cases with spirulina, tomato, the 1A and the 1B were like the bare minimum, like this is gruel and slop you're gonna eat for this. And then as you go up in power, it's like, oh, now we got some tomatoes and some like grain, and there's a lot more complex. And even at the higher ones, there's some fish, which turn out to be actually a really good idea, I think, in these ecosystems. And the key results, this was from his paper of just looking at it, and scenario 1A, that's kind of the bare minimum, 11 kilowatts. If you look at scenario 2, that's where you start to talk about more balanced diet type, like growing some vegetarian stuff, right? And then scenario 3 and 4, that's where you talk about actual some animals, and it's an incredible amount of energy. It goes from, I was saying 60 kilowatts before up to, you're getting close to a megawatt of energy per person. So it's incredible. I think I'll skip a lot of these, but I talk some about these. Bioreactors are pretty cool. On the moon, you have a lot of challenges because you can't use sunlight because it's dark for so many hours straight. On Mars, you have long dust storms. Something I really wanted to point out is that photosynthesis is inefficient, but there are synthetic biology options that can drive efficiency up. And there's a study out there that actually produced with electricity proteins, and they were talking about feeding the third world with these proteins, and I read it and I was like, no, you use electricity to produce protein for your space environment and you sell it to astronauts. Because if you can use direct energy, you basically increase your efficiency up to 10 times. So instead of needing, say, 100 kilowatts, maybe you can get away with 10. And there's some other cool ones like genetically modified tobacco that they have now 40% more efficient at making the bonds that it needs. So